Hi, welcome back. And then so in today's episode, we will go through a simple LRU cache implementation using TLA+. So on the right, we have the canonical implementation of an LRU cache in your typical LeetCode or design settings, right? So you have three things. You have the recency list, and then so the latest accessed element in the LRU cache will be at the tail of this list in this example, right? And then so basically as you access the keys, you sort of pluck it out from where it is in the recency list, and then you stick it at the end of the list to sort of indicate that it has been recently accessed. And then so obviously the key on the head of the list is the oldest one. That's basically if you were to evict it, it would be evicting the head of the list. To achieve amortized O1 access, when you update the LRU cache, we need a lookup table, right? We have to quickly figure out where the key is in the recency list, right? So here where we need the second data structure, the key to iterate to lookup table. So the key to iterate to lookup table is typically implemented using a unordered hash table to allow you to quickly figure out, for a given key, what is the iterator? Where is the iterator in the pointing to in the recency list? And then so basically when you're updating, the LRU cache, the recency list, you could quickly figure out, which key to access, which iterator to pull. And finally, the third piece of it is obviously given that it's a cache, you have to have a lookup implementation, or you have to have the key to lookup table itself, right? So that's the key to value lookup table. That's the third piece of data structure that needs to be implemented. So with that out of the way, so let's look at how we could actually implement this using TLA+. So in TLA+, this is actually, we care more about correctness, right? And then so the second data structure in the canonical implementation is for efficiency reasons, right? We need to do a quick lookup. We don't actually have this concern in the TLA+ model, right? In TLA+, we care more about, accuracy, right? Like correctness, right? And then given that, in a TLA+ setting, the model is likely much smaller anyway, we can take a bit of a shortcut, right? So we can actually omit the key to iterate lookup table altogether in our LRU cache implementation in TLA+. So let's turn our attention to the left side of the picture, right? So we really need three things, or two things really, right? And then so the LRU size is simply the size of the LRU cache that we want to instantiate. And then basically maybe, so this can be used as an independent module if you were to import it, right? And then so the size is ideally dynamically specified. And then on top of it, we have two things, right? We have the actual key value store, so that's the first variable here, and then which is so this guy is actually just implemented as a function, which is basically a lookup table in TLA+ landscape. And then the second is the LRU recency list. So this is to be implemented as a ordered tuple, right? So to sort of simulate that linked list behavior. So let's look at what happens when we insert something into the LRU cache, right? And then so really we have two broad cases, right? Either the key already exists or it doesn't, right? And in the case that the key already exists in the cache, then we don't really care about, whether the cache is full or not, right? If the key already exists, the space has already been allocated. We simply want to replace the value and then plug it from the recency list and then stick it to the end, right? And then so updating the recency list is done using this is done with this line here, right? So we use the select sequence on the recency list with a customized lambda or filter function, right? So we're basically looking at taking a look at the list. We take everything, maintain the order, except we're excluding the target key value, right? So we're sort of plugging it out first, right? And then so the remaining sequence is returned using is defined here. And then what do we do with the target value that we plugged out, right? The key that we plugged out, right? We stick it to the end, right? And then so basically with that, then we append the key using the append function. We append the key to the end of the sequence that we just received, right? And then so that's the new updated recency list. Okay, and then now we need to update the key value store, right? And then so that's done using it by simply iterating through all the keys in the LRU KV store, right? And then so the domain keyword here specifies we're only iterating through the keys, and then for every given key, what do we do, right? So if the key matches the target key value, then we set it to the value we have received. Otherwise, we use the value that was already in the key value store, right? So that's if the key is in the, so this is the case when the key is already in as it's a member of the cache, right? So in the case that the key is not in the cache, then we have two further different scenarios, right? So either the cache is not full, right? Or the cache is full. So in a case that cache is not full, it's actually pretty trivial, right? Like we don't need to manipulate the recency. Well, we still need to manipulate the recency list, but we just need to stick the new key at the end, right? And then so that's done using the append, right? Updating the key value store is very similar, right? The caveat, the difference is we're still iterating through all the keys in the key value store, but given that the key doesn't exist, we need to union the keys to include the key we're adding, right? And then so this basically increased the key space by one, by the one that we're going to add. And then the rest of it is the same, right? We're still replacing the key, if it's the key that we want, we set it to the value that was received. Otherwise, it's whatever it was before. And then now the final case where the key is not a member of the cache, but the cache is full. So this is the interesting case, right? Where we actually need to evict something, right? And then so that's implemented using this here. So yeah, so we're taking the recency list, and then we're still applying a lambda function to the recency list, and then but our filtering criteria now is basically anything but the first element, right? Everything but the head, right? So we're taking the whole thing but minus the head, and then so now this is effectively evicting the stale element, right? But with that, we still need to append the new key at the end, right? And then so on top of it, there's still an append function to append k to the end of the list, right? So this is updating the recency list. And similarly, now we need to update the key value store itself, right? And then so the first part of it is what we covered just a little earlier. We need to expand our key space by one, right? And then so we're unionizing with k itself, so we're including the new key, but we also need to evict the old key, right? And then so we're unionizing with the new key, and then we're evicting the old key by using the exclusion operator. And then again, right, the first element in the recency list. And then again, right, just to maybe just highlight this a little bit, right? And then so in the TLA plus specification language, anything with a prime variable is for the next state, right? So even though we're updating the recency list here, we're updating it to the recency prime, right? So that's the next state. And then so even though we're using the recency variable here, this is the pre-updated version of the recency list, right? And then so we're updating it here we're updating recency prime, but then for the second statement, we're still only referring to the current recency list. So this is still the pre-modified one. Okay, so that really is it, right? Hopefully it's not super not super confusing, I guess. And then so again, right, so you could do the usual, you could run it to make sure that it works as you expect it to, but oh, maybe we should cover the safety property a little bit, right? And then so basically the safety property here, I'm just picking the trivial ones. So we have the key value store, we have the recency list, but then the elements in both, the number of elements in both should match, right? They're basically guaranteed to be unique. And then so so basically the first line here is to make sure that the keys match, right? And then so on the right side of it, we're simply taking the keys, the domain keyword to sort of extract all the keys from the key value store, right? And on the left side of it, we're looking at the recency list. So the recency list is implemented as an ordered tuple, but I believe underneath the hood is actually a function. It's a number function, right? It's basically 1, 2, 3, 4, 5, whatever, up on, all the way until, and then whatever the size of the list is, and then the value associated with these numbers, I guess, are the keys, right? And then so we're using a basically this implementation to sort of pluck out the values of the recency list, which would be just the keys, right? And then so then we turn that into a set, and then that will match the keys of the KB store, right? And then the second thing here is to simply make sure that the key value store never exceeds the size of the LRU cache itself, right? And then so this is, if we run it as like this, then it should pass. So it's good, right? And then but we actually want to sort of characterize or qualify the behavior of the key value store a little bit, right? And then so basically this is just to force a callback, right? So when we hit the size, the maximum size we expect, let's look at the unwind stack, right? Just to make sure the behavior is what we expect it to be, right? And then so if you go to the stack a little bit, right? So basically we're inserting A first, followed by B, followed by D, followed by E, right? And then but you look at the recency list, this is the list that we expected, right? In the order that they were inserted, right? A, B, D, E. Yeah, that's all I wanted to cover in this episode. As usual, thanks for watching. Thanks. Bye.